Welcome to The Explainer. Today, we're diving into the invisible forces that literally power our modern world, electromagnetic waves. I mean, think about that for a second. Right now, all this stuff is just passing right through you. It sounds like something out of a sci-fi movie, doesn't it? But it's the real fundamental science behind how everything from your phone to the actual sun works. So, what's the big deal about these waves? What makes them so different from, say, a wave in the ocean? When you think of a wave, you probably picture something like a ripple in a pond, right? That ripple needs the water. Or, hey, the sound of my voice. It needs air to get to your ears. These are called mechanical waves, and they all need some stuff to travel through. But electromagnetic waves, they're totally different. They're the ultimate self-sufficient travelers. They don't need anything. And that's exactly how light from the sun can make that mind-boggling journey across the total vacuum of space to get all the way here.
Okay, so where do they even come from? Well, picture this. You take a tiny charged particle, like an electron, and you just wiggle it. You shake it back and forth. That acceleration is the key. It's the spark that creates this wave. And this wave is made of two parts that are forever linked, an electric field and a magnetic field. They're kind of like dance partners, you know? They're always perpendicular, always creating each other, and they can just keep that dance going forever, right across the universe.
Now, you might think something this fundamental was always known, but nope. The discovery didn't happen overnight. In fact, it all started with a really big problem that had physicists in the 19th century just scratching their heads. So back then, physicists had this really solid rule called Ampere's law. Super simple. Where there's an electric current flowing, you'll find a magnetic field around it. And it worked. For the wire carrying current to the capacitor, it worked perfectly. But then they looked at the empty space, the gap between the capacitor plates, and a compass needle placed there would actually move. There was a magnetic field. But how? There's no wire, no electrons are jumping that gap. It made no sense. The law just broke. This was a massive problem. I mean, it's a huge red flag in physics when a fundamental law just stops working. It told them that a huge piece of the puzzle was missing. It was exactly like finding smoke, but with absolutely no fire. And this is where our hero enters the scene. A physicist named James Clerk Maxwell steps in with an idea that wasn't just a small fix. It was a revolution that would change, well, everything. So Maxwell had this absolutely brilliant insight. He basically said, wait a minute, what if a current isn't just about moving charges? He saw that as the capacitor charged up, the electric field in that empty gap was getting stronger. It was changing over time. And here's his big idea. What if a changing electric field could do the exact same job as a real current? What if it could also create a magnetic field? He called this concept the displacement current. And folks, that was the missing piece they were all looking for. And this is the moment where everything just snaps into focus. It's this incredible feedback loop, like a perfect chain reaction. You have a changing electric field, which makes a magnetic field. But guess what? We already knew that a changing magnetic field makes an electric field. So they just keep making each other, over and over again. They literally bootstrap each other into existence, leapfrogging through empty space as this perfectly self-sustaining wave. So with that final, brilliant fix, Maxwell put it all together. He wrote down these 4 beautiful, elegant equations, and with them he described everything about electricity and magnetism. I mean, these equations are as important to this field as Newton's laws are to motion. In one go, he united electricity, magnetism, and, here's the kicker, light, into a single, unified theory. He basically figured out what light is. Okay, so Maxwell's equations did way more than just solve that one little capacitor problem. They opened up a whole new universe. His math predicted that there shouldn't just be one type of these waves, but an entire spectrum of them, a huge invisible family of waves, all traveling at the exact same mind-blowing speed, the speed of light. And here it is, the electromagnetic spectrum. It's literally all around us all the time. Down at the low energy end, you've got radio waves. Their wavelengths can be huge as long as buildings, and they carry our radio, TV, and Wi-Fi signals. Then you move up to microwaves, infrared, which is basically heat, and then you hit this teensy tiny little sliver that we call visible light. That's all our eyes can see. And as you keep going up in energy, you get to the really powerful stuff. Ultraviolet or UV rays from the sun, X-rays that let doctors see our bones, and finally, at the very top, gamma rays, super high energy waves from things like nuclear reaction. Now, the key thing to get here is the relationship between these properties. It's basically a trade-off.
The higher the energy and the higher the frequency, that's how many times the wave wiggles per second, the shorter the wavelength gets. So you can think of high-energy gamma rays as these tiny, super-fast, frantic vibrations, while low-energy radio waves are more like long, slow, lazy swells. Let that sink in for a minute. Every single thing you have ever seen with your own eyes, every color, every sunset, every person's face, all of that exists in just this one, incredibly narrow band of the spectrum. It means we're basically blind to almost all of the reality that's happening around us right now.
Okay, so we've gone from a weird physics problem to this huge hidden spectrum. But why does any of this matter to you? What's the takeaway for your daily life? Well, the short answer is pretty much everything.
I mean, seriously, our entire modern world is built on this spectrum. That smartphone in your pocket, it's using radio waves to talk to cell towers. The microwave in your kitchen, it uses microwaves, of course, to make the water molecules in your food vibrate like crazy and heat up. That TV remote on your coffee table, it's sending out pulses of infrared light. When you go to the doctor and get an X-ray, yep, that's another part of the spectrum. Even the light coming from the screen you're watching this on right now, it's all part of the same family. It is the invisible engine of modern life.
So think about that. It all started with one little question, one nagging inconsistency about a capacitor. And from that single puzzle came a theory that not only explained the mystery, but gave us the tools to build the world we live in today. It just goes to show you how one brilliant idea can completely change our reality. Which really makes you wonder, what other invisible forces are out there, just waiting for us to discover and harness next?